Okay, so at the end of last lecture, we did something quite impressive. I think we managed to produce a means through which, if we know the angle of any element, okay, the theta angle of the element, we can then determine the 4x4 stiffness matrix that enables us to relate global deformations, so that's u's and v's on nodes 1 and 2, and the forces that must be present because of that member on node 1 and 2 of that element. So we aren't quite at the stage where we can set up a whole KQ equals P problem yet, but we can determine the transformed stiffness matrices for each element. Okay, so I'm going to do a diagram. I'm going to do some coding today where we actually set up how to produce those 4x4 stiffness matrices for each element. So it's going to be a mixture of drawing and coding today. So this is looking at the same problem that we did by hand. We did this very manual method to make this problem work. We have node A, node B, and node C, and we called this one element 1 and element 2, which makes this theta 1 and this theta 2. So we would like to be able to produce the global KQ equals P problem for this problem just by having some information about where the nodes are and which elements connect which node to which node. So table, I think it's 4.3 in the notes. Let me just check what it actually is. In the accompanying notes, there is a table, table 4.2, sorry, and it's even available for download as a CSV, okay? That's how nice I am. So that table is available to download. Let's think about what that table actually means. So it contains information about each node. It contains the X location and the Y location, and then there's some information about each element. So element 1 and element 2. If I had been fully into Python when I started writing this course, I probably would have started numbering at 0. Doesn't really matter though. We're going to number like humans do. We'll say this is element 1 and element 2. We've got 3 nodes, A, B, and C, and these have X locations of, what are they? 1, 1, and 3, and 0, 1, and 2. So these just give us the geometry information. So it makes sense that A and B have the same X location because they're the same place horizontally. Node C is to the right, and then node A is the origin in terms of Y. We've got node 1 and we've got node 2. So this is obviously not to scale according to this table that I've drawn, but we're going to use this table. We then have got these second 2 columns that describe elements 1 and 2 and what they connect to. So we will remember that each element, this is some sort of arbitrary element, has 2 nodes. Connects node 1 to node 2. So we need a means to be able to tell our codes that we're going to write which elements, or sorry, say for element 1, what is node 1 and what is node 2. So element 1 goes from node A to node C, so it has a 1 and a 2, and I'll put a 0 anywhere else. So if there were more nodes here, they would just have zeros everywhere else except for node 1 and 2. And I've described it as going from 1 to 2. You could equally say that it goes from 2 to 1. Okay? But just for consistency, I tend to describe my nodes as going in alphabetical order, from A to C, for example. Element 2, we can see, goes from node B to node C. So we have a 0 in the A column, a 1 and a 2 here. So there's enough information here now to determine the 4x4 KE, the stiffness matrix for each of these parts, each of these elements. So let's just remember what that actually represents. So if this is an isolated element, it has node 1 and node 2, we said that there's 2 displacements. Now these could be lowercase, u1 and u2, and 2 forces, which we said would be F, x1, and fx2. So this is all in local coordinates. So then the stiffness of this element would be Ke 1, 1, minus 1, minus 1, u1, u2 would be equal to fx1, fx2. So this is the local stiffness matrix. Oh, sorry, this is not the local stiffness matrix, the local KQ equals P formulation, we'll say. So that's our local KQ equals P. Now what we want to set up is remember we transformed this into a global set of coordinates. So we said there were two deformations here. We've got uppercase V1 and uppercase U1, uppercase U2 and uppercase V2. Now these were related, U1 and U2, to the uppercase U1 and V1 and U2 and V2 are related to U1 and U2 through the transformation matrix. So we've already done that, and what we ended up showing was that we could produce a 4x4 stiffness matrix for each element, which we call the transformed stiffness matrix. Let's just write that down. Then be equal to KE, and then it's a big 4x4 thing. So I have a cosine squared, sine cosine, minus cosine squared, minus sine cosine, sine cosine, sine squared, minus sine cosine, minus sine squared. And then I can just copy these down, and I might have actually, yeah, for once I've drawn a matrix with enough space in it so my rows and columns line up. That might be the very first time I've ever done that. Okay, so we have this matrix here, and we remember that S is simply the sine of the angle of the element, and C is equal to the cosine. That's word on cosine, let's say cos theta of the element. So we can determine this part now. We can also determine the KE, because KE is just this local stiffness. It's just a scalar. It's got values of newtons per meter. So this is E A on L. So if we know the Young's modulus and the cross-section layer of the members, the length is actually determinable from this information here as well. So we can now, and what we're going to be coding up today, is how we make these 4x4 stiffness matrices. So I'm going to put this up here, and I'm going to open up a new Jupyter notebook. There we go. Okay, so hopefully this is large enough to read. It's like enormous old person font on my computer. We're going to use a few different packages today. We're going to import NumPy, because we always use NumPy. I'm going to use pandas to load up a table. Okay, that's just the way I'm choosing to do this. And then I am going to use SymPy for a few things. I'm not going to introduce symbols here, but there's one thing from SymPy I want to use, which is the ability to print matrices nicely. So I'm going to import SymPy as SP, and then I've got a bunch of things that I want to also include that's just going to help us maybe display a few things later. So I'm going to say from display, import display, and I think, do I use that? I'm looking in the code that I wrote this morning. I think I use display. Yes, I do. I use display once. That's fine. I'm also going to import math as well, because I want to be able to demonstrate the difference between using a NumPy square root and a math square root. I could import math as maths, just to make my own sensibilities feel better as well. So we've got all of our things imported now. The first thing we're going to do is we're going to import this connectivity table. So it's that table that is available. It's this thing here, available as a CSV. So let's import it. So I'm going to call it contable, and I'm going to make a pandas data frame. So contable is equal to pd.read CSV connectivity table. There we go. Because it's in the right directory, it's just in the base directory. I did a tab, it's auto completed, and I've got connectivity table at CSV. and then I'm going to use that handy display object, which I've imported from ipython.display. And I want to display con table. Let's give this a look. There we go. So we've got this table in here. It's exactly the same as the one that I wrote out. Okay, we've got this table here. 113, 113, 0, 1, 2, 102, 0, 1, 2. So we've got the table right, and we've managed to import it in a format that we can now use. So let's have a look at trying to work some things out. I'm going to make myself a function first, because I know that I'm going to have to do something twice in this object. I'm going to have to make this matrix twice, which means I need to make a 4x4 matrix that's just a function of, I just want this bit here, I don't necessarily want the KE. Okay, 4x4 matrix, it's just then a function of theta. So I'm going to define that as a function, because when I have to do something more than once, I'll make a function for it. So let's do make a function that creates the transformation matrix. We'll do def make transformed, we'll say, because it's not quite a transformation matrix, it's the transformed. And I'm going to be consistent now, and I'm just going to say with no KE, because I'm not going to include this KE in the function up here. I'm just going to include all of the things in here. So we can do def, make transformation matrix, make transformed matrix. That's going to be a function of theta. Okay, so let's make a doc string just for the hell of it. I'm off screen with this bugger. Okay, I need to go up. I'm writing the doc string there. Let me just do, I'm just saying what I'm relating. So this function takes the inclination angle of bar element returns 4x4 transform stiffness matrix relating global displacements to the element forces. Okay, so that's what we're producing. The bit that I've just written there, let me just explain what I mean by that. So we're producing this 4x4. Let's just remember what this means here, this matrix that we have. So this is our local problem, K, Q equals P. So that's my K matrix, that's my, well, this is my K matrix. That's my Q, and that's my P for this. So this is just a 2x2. When I've got it in this format here, then it becomes K, and then the Q becomes U1, V1, V2, and V2. So that's these U1, V1s. These green things here, okay, are equal to fx1, fy1, fx2, and y2. Okay, so those forces up here, if we just draw those on as well, this would be fy1, fx1, fx2, fy2. Okay, so that's what this matrix does, and that's what I mean by it relates these displacements to the forces. Now these are in global coordinates or the global directions, but these are still just only ever going to be 1 or 2 because they're related to the first node and the second node of the element that we happen to be dealing with. At the next stage, we're going to try and work out, is that A, is that B, or is that C? We're going to get to that hopefully in the next lecture tomorrow. So let's go back to the Python window. Okay, so we've got this matrix here. I now need to, well, it's the functions of sine and cosines. So I'm going to say C is equal to math dot cosine of theta. S is equal to math dot sine theta. You can do numpy as well, it doesn't really matter for these. If I just want to scale a value out, I don't want an array, then I tend to use the math. Let me just resize this window so it appears on screen properly as well. Okay, there we go. So I'm losing some of the bar. You don't need to see the bar at the top. That's fine, but then I just don't want the bottom of this to go off screen like it was earlier. Okay, so we've got those two things now, and I then just need to make an array. So my stiffness matrix is going to be, why can't I type? Let's try again. Ke is equal to empty.array. So I need to make a matrix, which is just an array, so it's cosine squared, sine times cosine, minus cosine squared, minus sine times cosine. That's my first row sorted out. Let's make the next row cosine times sine, sine squared. So this is just this matrix I'm making now. Here. Minus sine times cosine, minus sine squared. Okay, and then actually I can just copy these two now, and I should be able to just change these minus signs now. So let's do this, minus, 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 minus. These now become positives. And then just for consistency, I will space these over so it looks better. That should be good. And then this function just needs to return k. And I want to see what this looks like, so let me zoom this out of the way. Let's just see if this works. So we'll test it by saying theta. Let's make theta equal to 0 degrees, okay? Because we then know we should only get, if theta is 0, then my element is aligned with u. So I should only have cosine squared terms in there. I should have nothing in the sine squared term. So I should have something here, and something here, and something here, and something here. Okay, so that's what I should have in this matrix. So let's say theta is equal to 0, and let's do print make. Let's do this. Let's do k is equal to make transformed matrix theta print k. Doesn't like it because math is not defined, and I hoisted by my own smart ass petard. I won't import. No, let's do that. Okay. There we go. It's because it doesn't know what math is. Okay, math is not defined. It's because I imported math as maths to be annoying. So let's try that again, and now we've got my matrix here. Okay, and it's what I expected. It's we've got 1, 1, 1, well, 1, minus 1, minus 1, and 1 in here, which is what we wanted to see. Now, if theta was equal to 90, we should expect only to have the sine squared terms in here. No, we shouldn't. We should, but that's theta in degrees, and I should have turned it to radians. So let's say np.radians. Here we go. We've got effectively 0 in here. So we've got, let's have a look. We've got 1, 1, 1, and 1, but everything else is so very, very small. There's just some floating point issues in there. Let's see if I change it to np.pi and 2. Yeah, there's obviously some. Let's see if I change this to a numpy, cosine and sine, see if it does better there. No, same problem. That's fine though. It's not an issue for what we're doing. We still see we've got 1 and minus 1, 1, minus 1 and 1, which is what we want, and everything else is effectively 0 in here. These matrices look all right when they're printed like this. I think they look better when they get printed as SymPy matrices. Okay, so SymPy has something called pretty print in it, pprint, which means we can print a matrix, but it can only print SymPy matrices. So we're going to make a new function that helps us to print matrices a little better. So we'll see. We'll call def print matrix. It's going to print matrix in. So all it's going to do is going to do sp.prettyprint, and then it needs to make a SymPy matrix. And SymPy matrices start with a capital M of the matrix in. That's all it does. So now I'm going to do print matrix. Okay. So even though it's a little bit too wide because of all of that precision here, it just does a slightly nicer job of printing out that matrix. So let's see if we can round this to 7 decimal places. There we go. SymPy just does a slightly nicer job of printing that out like a matrix, I think, as opposed to there we go. So SymPy looks like a matrix. This is very clearly still an array. Now you've got to be careful with how we use this. Don't turn these matrices into SymPy objects because they then become a little bit complicated to deal with later. I just want to check I've done this properly. I'm going to do print type k. Okay, and it's still an ND array, which is good. Okay, whereas if I turned it into a SymPy matrix, I would get print type. Okay, I get something else. I get this horribly complicated SymPy.matrices.dense.mutable dense matrices. This means if your object type changes to that, it becomes problematic when we try and do NumPy matrix algebra later. So we don't need any of these anymore. All we want is these two functions. Okay, we want this function here, which makes a transform matrix for us, and then this one down here, which prints it for us. So now we are going to go through this problem, and we're going to try and determine what those two transformed matrices are for each element. So we've got element 1 and element 2, and we're going to do it by looking at this table and seeing how we can get information out of the table. So let me go back to the table. Let's put this down here. Let's get rid of these lines. Okay, so that's my connectivity table. So immediately from this table, if I had more elements, it'd have more parts along here. If I have more nodes, it'd have more rows. So I can see that in this format that I've got, my first 3 columns are always going to be node, X location, and Y location. So that gives me information about the number of elements. So let's work that out. Let's say determine the number of elements. We'll say any is equal to the length of contable.columns minus 3. Okay, because we want however many columns there are, take 3 away, that's the number of elements that we must have in this matrix. So then we do a print. Okay, system has 2 elements based on the connectivity table. This little / or that's actually a backslash, just enables me to continue the line by putting a line feed in. Okay, because I'm working in this very narrow window, it means that it doesn't introduce a horizontal scroll bar. I guarantee that more than 5 students will just copy that anyway and will always use that when they have this sort of line. Okay, I want you guys to think about why I'm doing things, and it's why I try and mention why I'm using this character here. It's just so I can continue that line. If I get rid of this, it will throw a fit because it knows that I'm still inside this string and this is a new row here. So I'll just put that in there because it enables me to change that, to put a line feed in without ending that line, basically. Okay, so now we need some further information. We need to know the Young's modulus and the cross-sectional area. So I'm just going to make up some numbers. Let's say could put E and A as symbols. I don't really want to do that because it makes the problem a little bit more annoying to do if we have symbols in here. I will give you guys an example where I've done it with symbols, but because of the problem we saw up here, when you change matrices to SymPy matrices, sometimes accidentally, it means you can't do some of the NumPy linear algebra with it that easily. Okay, but I'm going to set these as just numbers. So E is going to be what it usually is, which is 190 gigapascals, and A is going to be 12 centimeters squared. So let's run those again. Now what we can do is we're going to iterate on those elements. Okay, we're going to iterate on those elements. So I'm going to say, which basically means I want to go through this table, pick out this column, and do some stuff with it. Pick out this column and do some stuff with it. And then what we want to determine is the length of the elements and the angle of the element. And once we've got those two things, we can then determine the K matrix from this. And if we multiply it by E, by A, and then divide it by the length, we've then got that 4x4 matrix. So we're going to do that. So let's leap over the elements. For E in range any. Let's just remind you guys how this syntax works. So I'm doing there we go. I'm going for 0 and 1. Okay. I now want to be able to extract the columns from the table. So let's just do print on table of columns. Okay. These columns are called L1 and L2. So I need to be able to say the first time round, go through element 1, the second time round, go through element 2. So I'm going to say column name. Column name is equal to an F string, so I love using F strings. It needs to be E plus 1 expressed as an integer. Okay, that's then just that string there. So then I should be able to just print out that column table. Nope. And that should just print out that column, and I'm going to put a line feed after this. So print this out. There we go. So first time through, it's pulled out 102, which is correctly that first column. Second time through, it's pulled out 012, which is the second column. So that's what we wanted. It's actually the fourth and fifth, but it corresponds to those two nodes, which are the ones that I wanted. Okay, I don't need to print out that anymore. So what I now want to do is I want to find out which is the starting node and which is the end node. So I want to find out corresponds to node 1 and node 2. So I need to find which row there's a 1 in, and then work out, for example, when I found out there's a 1 here, I need to work out that corresponds to an A. Okay, for this element 2, where there's a 1 here, that corresponds to node B. So I'm going to do that using some pandas commands. Again, you don't have to do this the exact same way I'm doing it. This is just a means to go through a table and do things programmatically. And I choose pandas because I quite like pandas. Couldn't eat a whole one though. Okay, so find the starting node. So the first step is we're going to find the row. So let's extract this column. So let's say this column is equal to column name. No, it's equal to column table. Okay, so that's just pulled out that column on its own. Let's just remind ourselves what it is. Okay, so I've got those two now. So that's pulled that out. I now want to find where that equals to 1, and that's going to be the row corresponding to my first node. So we'll say the start node is equal to this column is equal to 1. And then the starting, sorry, that's not the starting node, that's the starting row. So let's do a print. Okay, so now it just gives me a Boolean index of where this occurs, but I can then use this Boolean index to say, okay, go back to this table here, look at this column, It's called node, and I want the Boolean index. So this first one is going to be node A, and the second one's going to be node B. Okay, so let's use that. So my start node is equal to con table start row. This isn't going to be the right value yet, but I'm going to show you what this does. Okay, so let's do print start node. So this allows me to pull out the correct row corresponding to the starting row. So this has given me the start row. I've printed out, I've called it a starting node. Now what I want to do is I want to say of this object, take out the node value. Now I know the next line I'm going to do is going to fail, but if I don't make this mistake, someone will make it later and it will cause problems. So I think I want to extract node from it, and using pandas I just insert that column name as a string index. Doesn't like it because it says key error node. Okay, pandas data frames are slightly related to dictionaries, and it says there ain't anything called node. So let's go back and look at print contable.columns. Now this happens a lot when you're importing comma separator values and someone's created them sloppily. Node actually has a space after it in the title. So if I go back up here, change this here, this now says node. So element 1 starts at node A, element 2 starts at node B. Now I only want the value, I don't care about the index. So I'm just going to say up here, dot values. If I run that, it then gives me a list. I don't really want it as a list, I just want the object. So I say, okay, I want the first item in that list. And it's got it. So now I can use this logic to say print and use an F string, elements E plus 1 starts at node start node. Element 1 starts at node A, element 2 starts at node B. Now, that was not particularly impressive what we did, but imagine you had a massive table now. You could now get the starting node of every element just based around that table. You wouldn't have to manually go through and do any of it. So we can find the starting node, we can now do the end node. That's exactly the same. I'm going to copy these. Then I'm going to change the names, let's say end row, end node, end node. I need to change this to 2. Let's check if this works. Okay, because I use this line continuation character here, and then I put a line feed in. Because this was in a loop, it has indented it suitably. So if I remove that indent, I should get rid of this space down here. There we go. Element 1 starts at node A and ends at C. I should put at least one space in there. Element 2 starts at node B and ends at C. That's pretty cool what we've just done. Okay, so now that we've done that, we can determine the length of the elements. Okay, so if I've got an element that goes from anywhere to anywhere, I've got an x1, y1, x2, y2. Okay, this is always going to be a right angle triangle. So here, this is going to be y2 minus y1, x2 minus x1. That is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so I can always do that, and I can get those elements. Now that I know, and I've got my start row and end row indexes that enable me to extract things, I can do the exact same thing with the x and the y's. So down here in this table, it tells me I have x and y's, and those are these indices here. So these are then geometry information I can use to determine the length of the element, and I will then later use it to get the angle of the elements. Let's keep that down there. I'm going to print more stuff out in there. So determine the length. So x1 is equal to, how am I going to do this? So I need to do something similar to how I did this, but instead of pulling out x, instead of pulling out the node, I want the x in here. So if I take this out, let's take this one here. x1 is equal to contable, start row, and we want the x. Let's just check this runs, doesn't cause an error, so that's running. Now, I'm pretty sure this is going to work, so I'm not going to bother changing things. I'm not going to print out intermediate rows. So that gives me my x1 and my x2. And I now do the same thing for y1 and y2. Let's check what this looks like. So I'm just going to print these out as an intermediate step because I shouldn't be so cocky with my coding. Okay, so element 1 starts at node A and ends at node C. Now it says I've got x1 is 1, x2 is 3, y1 is 0, and y2 is 2. So let's just check that works. Element 1 starts at 1, x1 of 1, x2 of 3. That makes sense. So I'm happy this works. I can now determine the length from this. L is equal to p dot square root. Okay, so I've now determined the two lengths of those two. Now I know those numbers are correct because I've done this problem before. So we are able to do that from here. Now I've used a NumPy square root here. Let's just do a quick print of L. Okay, those are still scalars, that's good. Sometimes this can produce an array value if I'd done this slightly differently, and then that might cause a couple of problems later, but we look like we're okay. The angular orientation of the element we can get from the, well, anything. We get it from the sine rule, cosine rule, tangent rule. We now know L, so let's use this is my theta, so cos theta is equal to adjacent and hypotenuse, so that's going to be x2 minus x1 on the length. Okay, I avoid using the tangent, arc tangent, because it can go to infinity, so we have problems there. Okay, so let's check what that looks like. There we go. So I've got these two angles that come out, and let's just print those out as well. Let's see if they become useful as length, whatever meter, and is that angle. mp dot degrees theta. Let's put another line feed in here. How do I do I can't remember how to do a degree symbol using the keyboard. Doesn't matter. Let's zoom back in again. Okay. There we go. So this first one is at 45 degrees and the second one is at just under 30 degrees. And again, I know those numbers are correct, so that's good. So we've now got everything we need within here to be able to determine those matrices. So we've got all that information. Below here, I'm going to determine the material stiffness. Determine the element stiffness, I should say. That's just a scalar. That's a sampler. It's just a scalar. So Ke is equal to, let's call it Ke. E is equal to E multiplied by A divided by L. Okay, so I've now got, yeah, this sort of makes sense. So this element is quite a bit longer, so it's got a smaller total stiffness, okay, because it's just going to be E divided by A divided by the same thing. So that's fine, so I've got the stiffness coming out there. Now what I want to do is, now I've got enough information, I can get the transformation matrix. So I need to take this number, because that number that I just produced is this one up here. I need to multiply it by this, so I can use that function I created to get this and multiply it by that. So let's go through this. Let's say, make the 4x4 transformed stiffness matrix. Let's call this KE. At the moment, actually, let's call this KE. That's fine. Is equal to KE multiplied by, what did I call this function? I called this function make transformed matrix. And I need to put into it that angle that I've just determined. And then I defined, I think it's print matrix. Bingo. Okay, so we have got those two matrices now. That's good. This one up here, this makes sense. This is element 1. It's an angle of 45. So I've got the same terms in each of these. Okay, and if we, if you're struggling to think about why, then we can just look at math.acos. Let's do np.degrees. No, let's do np.cos, np.radians 45. Okay, 1 over root 2 for both of them. Okay, so we've got, that's why this is then a symmetric matrix for that first one, and the second one is an asymmetric matrix. Now what we've done here is quite impressive. We've now automatically been able to create those 4x4 matrices based upon this. So this code that we've done is not particularly difficult, but we've demonstrated that we've been able to produce this. Now what we're going to be able to do is we're going to go through the problem next. We need to work out, how do we take these, how are we going to expand them into a 6x6 so we can add them together. Because if we can remember, for this global problem, we're going to end up with a 6x6 matrix that we need to work out somehow how to add these two together to produce that. So I'm going to leave that bit for next lecture. Hopefully this has been a good and followable, it's been a reasonable introduction to how we start to code up some of this stuff. Please, please, please code this stuff up yourself. Don't just take the examples from the accompanying notes, because if you do that, you'll fail this course and you'll make terrible engineers, or you won't make engineers. Okay, code this stuff up yourself. I can't stress any more how important it is. Guys, I hope you're having a wonderful week. Look forward to seeing you all in the review tomorrow, and I will catch you all soon. Take care.